Welcome back. Welcome back, guys. Sorry for the late start here. A little bit of a technical problem. Anyway, um, we got a couple more starting up here. All right. Well, first things first, I'm going to share the calendar just to make sure again that everybody's on the same boat. Today's the second. You can see now that the assignments are getting a little spread out. We're roughly going to be doing one, maybe two assignments per week, and the average one. Okay, we do have another exam coming up, scheduled for, looks like the 23rd. Okay, and unfortunately I got to move that chapter 9. I just realized that's the spring break. So we're gonna have to make that do. Let's see, we'll cut her hair on the 22nd. So you looked out there. Okay. I looked at it. Yeah, because spring break starts on the week of the 14th, and then we're back that following the 22nd. All right. So, all right. Well, let us continue with the fun, right? Chapter 8, nomenclature. Now, we've been doing nomenclature as we progress. Well, basically, what I'm doing is introducing you to the naming of the compound. That's what nomenclature is all about, the name of the compound. And we eventually want to get to the point where you can be given the formula, and we started introducing you how to write formulas, how to create the formula of the compound, and then give it a name, okay? Or vice versa, back and forth. Either you have the name, give it a formula, you have the formula, give it a name. That's what nomenclature is all about. Now, there's a couple of things I want to share with you. Is the periodic table, the old-fashioned periodic table, specifically this one. Okay, I used it before, and here, let me go through this again. Now, we're all, hopefully by now, you're aware of where the metals are and where the non-metals are. If not, review that stir step to help you out. Okay. We also know by now that metals want to lose electrons and non-metals want to gain them, which means that all metals, when they become ionic, specifically cations, will have a positive charge. The question is, how much of a positive charge? And I've been using the term charge, but we're also going to change that name to oxidation number. Oxidation number is nothing more than a fancy name for the charge. Now, there are 16 elements, okay, that of the metals in hand that you would know 100% of the time their specific charge when they become ionic, okay? And I put them in red here. Group 1, all have a valence electron of 1 valence electron. They're metals, they're going to lose that 1 valence electron as compared to trying to pick up 7. They're going to lose 1, much easier energy-wise, okay? What's happening, you if recall, by losing that 1 electron, they now have their next layer, which is full with the octet. The driving force is the octet, obtaining the octet, 80 electrons around the outermost shell. So there are 6 metals there, lithium on down, that always will have 100% of the time a +1 charge. Next neighbor, the group 2, starting with beryllium on down, 100% of the time will always have a +2 charge, okay? Then there's 4 more. So if you count those, that should be 12, total 12 metals. And then we're going to add 4 more, starting with aluminum, number 13. Aluminum will always have a +3 charge. It's in group 3 valence electrons. It will always have a +3 charge. And then catty corner to that, diagonally to the left, you have zinc, number 30. okay, always will have a +2 charge. Silver, continuing diagonally to number 47, Ag is silver, always will have a +1 charge. And then we cut back to the right and we end up with Cd, cadmium, always will have a +2 charge. So there you have it. 16 elements, call them the sweet 16. 100% of the time, you know their charge. What does that imply about the rest of the metals? Is they vary. In fact, they vary from a +1 to a +9, and it all depends on the conditions. And because they vary, we have to name them using a different method, and we use Roman numerals, okay? So don't confuse those Roman numerals that we're going to use to name what oxidation number the metal is with the Roman numerals on top of the periodic table, okay, in the group. Totally different. And so, for example, copper can exist either as a +2 or +1, depending on how many electrons it lost. And so we would designate copper 2 with copper, parentheses, Roman numeral 2, in parentheses, okay? We'll have some more examples here in a bit. Okay, so that is also important to know that the 16 here, because the other ones have a variable oxidation state, we have to name them or call them out with that Roman numeral. We have to use the Roman numeral to tell you which one you're using. The 16 do not need Roman numerals, okay? I repeat, the 16 do not need Roman numerals in their naming. Okay. Now, the other aspect is these polyatomic ions here in the bottom left-hand corner. We'll be using them. Now, those polyatomic ions are a packet. They're a unit. They stay together. We don't separate them. If we need to use more than one, what we do is we put parentheses around the whole packet, okay? And then we put a subscript on the outside parentheses, the outside far right parentheses, and that subscript designates how many of these packets we need. Now, when we go, let me go back to the anions. And I'm going to just focus on the ones that are used quite often. And for example, nitrogen and phosphorus. Okay. These are nonmetals. And so when they become ions, they gain electrons. Okay. Nitrogen and phosphorus, they're in group 5. When they become ions, they gain 3 electrons. Oxygen, sulfur, selenium. So, okay, when they become ions, because they're in group 6, they have a -2 charge. And then the halides, all of them, I'm just going to stop at iodine, they are in group 7, so they become a -1. Now, we changed the name when they become ions. So nitrogen becomes nitride. Phosphorus becomes phosphide. Note the trend. Oxygen becomes oxide. Sulfur becomes sulfide. Okay. Fluorine becomes fluoride. Chlorine becomes chloride. Bromine becomes bromide. Iodine becomes iodide. Okay. Now I mention this because going back to the table, the polyatomic table, you notice we have nitrate and nitrite. Now, the naming is crucial. You're going to be very specific. If we dealt with the nitrite, it is just a -1, right? Everybody agree on that? Okay. And we call that nitrite. So the term IDE, nitrite, tells us that we have nitrogen all by itself. Okay. If you see nitrogen and immediately following that nitrogen atom, you see oxygen. Right after nitrogen, and you see oxygen, you're dealing with either a nitrate or a nitrite. Notice here, we got nitrogen there, and then immediately following that, we have oxygen. Specifically, we have 3 of them. And that polyatomic ion is called nitrate, ATE. Same is true for nitrogen. You see nitrogen, and then following that, you see oxygen, and there's 2 of them only. Then that is called nitrite. Notice the same trend is when you're dealing with a sulfur. Sulfur, when it becomes the ion, is called sulfide. Now you got sulfur by itself, and immediately following sulfur, you got oxygen, and 4 of them. Now you're dealing with sulfate. Okay. And so the 3 terms there, nitride, nitrate, nitrite, sulfide, sulfate, sulfite, very specific. The name itself tells you what you're dealing with. Okay. All right. So, excuse me, even phosphorus. In this case, if you got phosphorus all by itself, it's phosphite. But immediately following phosphorus, you see an oxygen. Specifically, you're going to see 4 of them. Then that is a polyatomic ion, and it's called phosphate. Okay. So the naming is important because why? Because you might be given a sentence or 2 describing a reaction using these terms of nitrate, potassium nitrate, and from the name, the nitrate, that would direct you to the polyatomic ion table, which directs you to the formula. Okay. All right. All right. So when it comes to naming the metals, we don't change the name. Okay. So the sodium element, it's a sodium, we call it the sodium atom or the element. Okay. So on and so forth. It is the anions. It is the anions that when they become ions, we change the name. And we just went through that example with sulfur becoming sulfide. The halogens, remember fluorine, chlorine became halides, IDE. Okay. So before we said be familiar with the first 20, but we're going to add a few more. Maybe some are repeats, but some are new. Ba is barium. C, little lowercase o is cobalt. Okay. I is iodine. Cu is copper. Fe is iron. Pb is lead. Hg is mercury. Ag is silver. Au is gold. Zn is zinc. Sn is stannous. And you might be familiar with stannous. Maybe this morning when you brush your teeth, you probably use some of this stuff. Look at the label of your toothpaste. You'll see it called stannous fluoride. So remember, next time you're brushing your teeth with tin, because the other name for stannous you can use is tin, Tin. Then we got strontium, nickel, bromine, chrome, manganese, and cadmium. Okay. Cadmium. Now, we're familiar now with ionic compounds and covalent compounds. If you're not, you really got to grasp this concept. An ionic compound, which is related to the ionic bond, is a combination of a metal and a non-metal. And you must know which ones are metals. Again, based on the periodic table, you at a glance determine what they are, if it's a metal, okay, and where the non-metals are. Remember that stair step, that is with the metalloids, okay? Metalloids are the ones that have properties of both metals and non-metals, hence the metalloids. Covalent compounds, combination of non-metals only, okay, also called molecular. So it's important that you're able to distinguish the two and identify if I have a covalent or ionic compound. And why is that? Because when it comes to naming compounds, nomenclature, okay, ionic compounds do not use prefixes. Covalent compounds do use prefixes. For example, CO2, we're all familiar with that. What do we call that? Carbon dioxide. Okay, that's a covalent compound. We use prefixes. CO, carbon monoxide. Okay, we use prefixes. Now, the only exception to that will water, H2O, because technically the name of water, the scientific name of water is dihydrogen monoxide. In fact, it's really kind of crazy. If you go on the internet and do a search for dihydrogen monoxide and the hazards of it, you're going to find all kinds of crazy stuff out there. And they're talking about the hazards of water, which could be a problem if you don't know how to swim. You know, that could be a problem. All right. So monoatomic ions, as we know, just simply the name. It's just a sodium ion, the chloride ion, the calcium ion. With no name change there, and the names for the metals remains the same. The polyatomic ions, as I stated within the table, and we're only going to use, there's a multiple polyatomic ions, but the most common that we're going to be using are in this table here. Thing to remember again is they are a packet. We don't change them. That's the name for that polyatomic ion, and that is the formula. And that is the corresponding charge. Okay. Now, because that part's going to be important when we start putting these molecules together. And I've introduced that earlier, but I'm going to kind of expand on it some more. Okay. Oxidation state, just a fancy name for the charge. So I've been using what is the charge of the sodium ion. Now you will hear the term, what is the oxidation state for sodium? Okay. For the sodium ion. Listen to the words. If one's asked, what is the oxidation for these? What's the oxidation number for the sodium atom? What do you think your response would be? Or compared to the oxidation state of the sodium ion, is there a difference? Yeah, because the sodium atom is the element, and its oxidation state, as the case of all 118 elements, is 0. Okay. Why? Because they have equal number of positives and equal number of negatives. The ions are different. They're either going to have negative or positive. Okay. And so their oxidation states kind of vary. All right. So all elements, as you know, or should know, have an oxidation state of 0. Okay. And we know the elements, when they lose or gain electrons, are going to have a new oxidation state. Okay. We got 16 elements that I just mentioned that have fixed charges. They have fixed oxidation states. Okay. The others are variable. So copper, like for this example, there's copper 1 and copper 2. Iron is iron 2, iron 3. Lead could be up to +4. I mean, the oxidation state can go from a +1 to a +9. Depends on the metal. Okay, and we have to find a way to designate those, and we're going to learn this. This is rehashed. We know metals lose electrons, become cations. Okay, we went through this. Refresh your memory, group 1A, and this is only true for the A elements. Group 1A +1 charge, group 2A +2 charge, group 3A +3 charge. Okay. I told you about zinc and cadmium always have a +2. Silver always have a +1. Okay, so that adds up to 16. You add those elements, 16. They have a constant oxidation state, and everybody else varies. Okay, so you can have, here's some examples here. Copper again, copper 1, copper 2. Now, what do we do? If you look at that, we got to designate copper 2, we write it with a Roman numeral. So you'll see it, the name copper, and then parentheses, the Roman numeral 2. If we look at iron 3, that would be designated as iron, and then parentheses, the Roman numeral 3. So that's important. Remember, when Roman numerals are used right after a name, That Roman numeral pertains to the oxidation state of the metal. Has nothing to do with the other guys, the other anions, only for that metal. And you need that information so you know how many uh, of atoms or ions to put together, okay, to make the formula. Okay. Anions, we know about anions. Again, they gain electrons. Group 5, I went through this, is -3. Group 6, -2. Group 7, -1. Okay, with respect to the nonmetals, they're gaining electrons. The driving force is to become isoelectronic with the noble gas in front of it. Okay, I noticed in some of the in the exam that people were making comments like, by gaining electrons, they become the noble gas. No, they do not become the noble gas. They become isoelectronic. They share the same number of electrons as a noble gas in front of it or the noble gas behind it, depending if it's a metal or non-metal. To become a noble gas, they have to lose protons or gain protons. We're all aware that column 8 has oxidation state of 0 because they don't react. Okay, for Chem 130, noble gases do not react because they have the octet. When fulfilled, helium has the duet rule. Okay, duet rule. So we're going to start dealing first with the metal and non-metal combinations. These are the ionic compounds. Okay, we're going to be looking at formulas and naming and writing names for these ionic compounds. Okay. And I'm going to go through a systematic approach when you go through this. Eventually, you can develop your own system on how you want to put them together to name them. My suggestion is follow a systematic approach until such time that you're comfortable. You don't have to, you can bypass some of the steps. Okay. Like riding a bike, you first start, you're kind of waggling here and there, and then eventually, you're going 50 miles an hour. Okay. So now, when we put these together, I mentioned this before, when we put the cation and the anions together, their sum should equal 0. So we got to put enough positives and enough negatives to equal to 0. Now, what I'm going to do is give you a general formula that fits for all conditions, because some of the homework does not end up being with the overall charge, the sum of the charge equals 0. And it's real straightforward, okay? So number of cations plus the number of anions must equal the charge of the molecule / compound, whatever it may be. Okay. Oh. Okay. So the number of compounds, the number of cations, plus the number of anions must equal the overall charge of the molecule. 9 times out of 10, the overall charge of the molecule is equal to 0. But you may need this situation where the overall charge of the molecule may not equal 0. Okay. For example, if we do SO4, the sulfate anion, okay, from the polyatomic ion. Okay. Now, in this case, the question might be, well, what is the oxidation state of sulfur when it is combined with other oxygen, SO4? Well, if it was sulfur by itself, the ion, we can go up to the periodic table and figure it out. But here, sulfur is the central atom and the oxygens are bonded around it. Okay, so we don't know its oxidation state as a sulfate ion, but we can calculate it because we can set up a very general and simple algebraic equation. S is the oxidation state of sulfur. We don't know what it is. Plus, that's the cation, okay? Because normally the central atom is the cation, the one with the positive charge, and everybody else around it ends up with a negative charge. Oxygen is in the oxide state here. It's still oxide. And we know that oxygen has a -2 charge, right? And there's 4 of them. So -2 times, oh, let me let that in here. -2 times 4, guess what that is? -8. And the overall charge is a -2, right? Because it's the polyatomic ion. Guess what? You can calculate now the oxidation state of sulfur when it is bonded with 4 oxygens and it has an overall charge of -2. So the point of this general equation I gave you is that you can use it for a multiple of different conditions, not only for a compound that has a neutral 0 overall charge, okay? So number of cations plus number of anions equals the overall charge sodium of the compound / molecule. So in this case here, sulfur would have, what would sulfur have? A +6, right? If you were to calculate that, sulfur will have an oxidation state when it is bonded with 4 oxygens and it has a whole overall molecular charge of -2. Sulfur itself has a +6 charge, which is different from sulfide that has a -2 charge. See that? All right. Let's work. Let's move on. All right. So now we talked at length about the polyatomic ions. Thing to take away from there, they are units. If we need to add more than one, we put parentheses around the whole unit, okay, the whole group, and we put a subscript on the outside parentheses, far right parentheses, okay? Now, so in this case, when we're dealing with ionic compounds, the compounds are going to end up to be neutral. So we need to add enough cations and anions to equal 0, okay? So here they start off with, okay, combine sodium and nitrogen. So step number 1, they're going to give you the element. Step number 2 is find the charge of that element. We know that sodium is in group 1A and will become +1 when it becomes ionic. We go and look for nitrogen, which is in group 5. It's a nonmetal. So when it becomes ionic, it will be a -2 charge on it, okay? And so now we got the elements in ionic form with their charges. So now we know how many of each we need to put together to write a formula, okay? Because we need to add them with enough of each to cancel out. So since sodium is a +1, nitride's a -3, I need 3 sodiums for 1 nitride, okay? And that gives me the formula that 3 becomes a subscript for sodium. And so now I have Na3 subscript 3 nitrogen, or in this case, nitride, because we're dealing with the ion. Now I'm going to add the name to that. In this case, it's simply sodium, again, because the metal name doesn't change. Nitrogen became nitride. So the name here is sodium nitride for that formula of Na subscript 3N. Okay. And so learning the name is important because you could be given the name and asked to give the formula, or be given the formula and be asked to give the name. All right. So let's check this one out. Two things. Okay, so you're given the elements. Okay, step number one, there's the elements. Step number two, take those elements you're given and put them into ionic form. And so we already did sodium. So we know sodium has a +1 charge. And sulfur, we don't know what it is, but we go find it on the periodic table. And it is in group 6. It's a nonmetal. So when it becomes ionic, guess what? It becomes -2 because it is in group 6 and it's going to gain 2 electrons to get that happy 8. Okay. And so now I need, you can see here, I need to put them together such that we end up with 0. So because the sodium is a +1, that tells me that I need 2 of them. So I need 2 sodiums for every sulfide. And the name would be sodium sulfide. Okay. So that 2 in front of sodium becomes a subscript. And there's a formula, Na2S. Okay. Hopefully you can start seeing the little trend here. Because one, if I got the formula, if I forget the charge on the sulfur and the sulfide, I can remember sodium's in group 1. It's a +1, and there's 2 of them. So that infers that sodium has become a -2 for the sulfide. Okay. All right. Let's try the next one. You're given magnesium and oxygen. Okay, so we got to go find out what the ionic form is, and we know that magnesium is in group 2, so it will have a +2. Oh. And oxygen. Oxygen is in group 6. It's a nonmetal. So when it becomes ionic, guess what? It would have a -2, right? Name, the metal name does not change. It's magnesium. The oxygen name did change when it became ionic. It went from oxygen to oxide. Okay, so I got the name. Okay, I also noticed that magnesium has a +2, oxygen has a -1. I put them together in a 1-to-1 ratio. They cancel each other out. So the formula is a straightforward 1-to-1 MgO. Okay, MgO. All right, here we go. Here we go again. Some more. Okay, we got potassium. Potassium is in group 1. So when it becomes ionic, guess what? Oh, it's a +1 ion, correct? Phosphorus. Phosphorus is a group 5 element. It's a nonmetal. It is going to pick up 3 electrons to get to the happy 8. By picking up 3 electrons now, it has a -3 charge. Okay? That is ionic phosphorus, has a -3 charge. So I got to put them together. That means that since phosphorus has a -3 and potassium has a +1, I need 3 potassiums. So I put a 2 up there, 3 up there, just to remind me as I work it through my system here, that 3 becomes a subscript. And then in my name, potassium, that doesn't change, but the phosphorus went from phosphorus to phosphide, just like the oxygen went to oxide, the sulfur went to sulfide. So you can see that the IDE ending of the anion is telling you that the prefix or the IDE is the atom by itself. Sulfur by itself is sulfide. Oxygen by itself is oxide. Phosphorus by itself is phosphide. And then when you start adding the oxygens after those guys for sulfur and phosphorus, that is where you start getting the polyatomic ions, okay? And the 8 and the I. All right, so here we need 3 Ks and 1 P. So our formula is K subscript 3 P. Okay. Now, right now, I'm just going what I'm given, but don't forget, you can mix and match here as we're progressing. We did sodium with sulfide, but you know what? You can do sodium with oxide, sodium with the phosphide. The same with magnesium, magnesium with the sulfide, magnesium with the phosphide, and potassium with the sulfide, and potassium with the oxide. So you can start mixing and matching these cations and anions. So you're starting to build up a database of these compounds that you're putting together. Okay, this is going to be a little more challenging, but I know you got it here. Why is it going to be challenging? No, well, maybe not. Okay, we got calcium and nitrogen. First thing we do is we put them in ionic form. So we got calcium, which is in group 2. It's a metal, so it will have a +2 charge. Nitrogen, okay, is in group 5. It will be a -3 charge. So now it's a little bit different now, right? Because before you're pretty straightforward. Either I put them 1 to 1, or I had one of the other and I just add more of the other to put them together. But here I have one that is a +2 and one is a -3. Okay. And so I just can't simply just put them together 1 to 1. If I put them together 1 to 1, 1 calcium, 1 nitrogen, I have a -1 left over. Okay. So I can play with the numbers if I want, or I can think of common numbers. Okay. For example, if you were going to add the fraction 1/5 and 1/7, I can't add them directly, right? I need to find a common number to add those two fractions together. So 1/5 and 1/7, convert everybody to maybe 1/35, right? All right, well, similar here. I got to find a common number for both of these ions. So can you guys think of a common number that it's
6.
used? 6 sounds reasonable, right? Yeah, sure can. And so, yeah, exactly. That means I need 3 calciums. Oh, 3 calcium. Oh, come on, my 3. Where's the 3? That gives me a total of +6. And I need 2 nitrites. Yeah, exactly. You got it, right? And so our common number here is 6. So I got to have enough of each so they cancel each other out. So I need 3 calciums and 2 nitrites. Now, naming wise, well, nothing happens to the calcium as usual. Okay, so it's calcium, and nitrogen became nitrite as it became the ion. Okay, and those numbers in front of the ions become the subscript. So the formula is Ca3 and 2. Now, if you look at a little trend here, it might help you. Check this out. If you look at the subscript of the nitrite, which is the 2, well, wasn't that the charge of the calcium? Yeah. And if I look at the subscript of the calcium, which is a 3, well, wasn't that the number for the charge on the nitrite? And so you basically you could use their charges to find the corresponding subscript. And at a glance, you can see that calcium, looking over at his partner, there's 2 of them. That tells you I got a +2 for calcium. And looking at nitrogen, I got a -3 for the nitrogen or nitrite. Okay. Sometimes that comes in a little handy, but remember that little trick there, that common factor, because you'll find other examples very similar. Now, notice the names so far that I've been doing. Sodium sulfide, magnesium oxygen, even calcium. Straightforward name, calcium nitride. I did not say tricalcium dinitride, okay? Nor did I say tripotassium phosphide or disodium sulfide. I didn't say that, okay? Because ionic compounds do not use prefixes. Second of all, I did not use Roman numerals here, okay? Notice no Roman numerals for sodium, magnesium, potassium, or calcium. Why is that? Because those guys are part of the 16. They have a constant oxidation number. They're not variable. Therefore, I don't require the Roman numerals. It's by default. It is what it is. Everybody in the world knows that sodium has a +1 charge, okay? And calcium has a +2 charge. It's not necessary to add Roman numerals. So far, no Roman numerals and no prefixes. Okay. Aluminum, similar scenario. You're given the atoms. What you do, you break down the atoms to the ions. Okay. We know that aluminum is a +3 ion. And the chlorine becomes an ion with a -1 charge. Okay. It's in group 7. Aluminum is in group 3. It's a metal. It's going to lose those 3 electrons. Chlorine is in group 7. It will pick up 1 electron to have 8 valence electrons. So it becomes chloride. And so now I can put my coefficient there and say, okay, I need 3 chlorides for every aluminum. Okay. And my name is aluminum. And the chlorine name changes to chloride because I'm dealing with the ionic chloride. So aluminum chloride is the name. I need 3 chlorides for 1 aluminum ion. So I have the formula AlCl3. Okay. And notice again the little trick we did up earlier. If you look at the 3 of the chloride, well, isn't that the charge of the aluminum? Yeah. And aluminum, there's no number there, but it's understood to be a 1. Okay, when there's, like in mathematics, when there's no number there, it's understood to be a 1. So the subscript for aluminum is a 1. Isn't that the charge for the chlorides, each individually? So at a glance, you can very quickly determine what kind of charge you're working with respect to the ions. Okay, so we got zinc, similar story. Break down the ions first. Okay. Zinc is one of the 16 I gave you, always has a +2 charge, even though it's one of the transition metals, the inner transition metals, always has a +2. And iodine, when it becomes ionic, always has a -1, just like the chlorine, the bromine did. Okay. And so very quickly, I can see that I need 2 iodine or iodides now, because that's what it's become for zinc. So the name simply is zinc iodide. Okay. Just like the iodide you use in your table salt. Next time you look at a bottle of iodide table salt, you're probably using potassium iodide or sodium iodide. And that's what you use to help your thyroid necessities. All right, so there's our formula. Okay, so keep track. Now, at this point, if you think about it, I can interchange all the anions and the cations. So I got 6 entries, and so I can make 6. I can go sodium sulfide like we did, but I can go sodium oxide, sodium phosphate, sodium nitride, sodium chloride, sodium iodide. That's 6 combinations, okay? And then I can do with the other, I can go magnesium sulfide, magnesium phosphide. So right now you got 36 compound mixtures that you can put together already. I can play with all the cations and change the anions. Okay. So at this point, you're about 36, and then 36, and then the same with well, you got nitrite in there already. So yeah. So you're building up in your database of all the compounds you're gonna be up to a few hundred compounds. Okay. Now we got something a little bit different now. Okay. You see a Roman numeral. That should give you a flag. Roman numeral. Okay. Now we're dealing with the other non-sweet 16 metals. Okay, because they're telling you here, you are using copper 2, Roman numeral 2, which tells you that you are using copper with a +2 charge. And oxygen, like we did with number 2, always has a -2 charge. Okay. Okay, so the Roman numerals +2 charge, the oxide, which is a -2, we can very simply put them together. Okay, but to name them, we have to utilize the Roman numeral. So copper, Roman numeral 2, and then the oxygen becomes oxide. Okay, and that is the name of of copper 2 oxide. And that's our formula, straightforward 1-to-1, because the copper is a +2, oxide's a -2. I can put them together as a 1-to-1. Okay. And its name is copper, Roman numeral 2. Now you don't have to put a space after the R in copper. You can, it's not going to hurt it. We've been training Canvas to recognize the space after copper, the term after the letter R. But if for some reason Canvas counts you wrong and you wrote it copper 2 oxide, let me know. I'll definitely give you the points. Yeah, with the space or not, it's correct. Okay. All right. So here we have another one. We got lead 4 oxide. So first thing we do, write the ions. So we got lead, Pb. It's telling us that we're doing a +4 ion. That's what that Roman numeral is. Okay. And oxide hasn't changed, still the same, -2. Okay. So that means that I'm going to need 2 oxides to cancel out the +4 from the lead. So that 2 becomes the subscript for the oxygen. My name's lead, Roman numeral IV 4 oxide. And there you go. There's a formula. So the Roman numeral is very, very important. Okay. Okay, very important, because in this example, let's do number 7, do another example of 7. What if you were given 7A, number 7A, and they said Cu and O, okay? What if they said that, okay? Well, that means that they're using copper 1 oxide. And so when we write the ions as Cu +1, okay, plus the oxide, which is a -2, okay? That's our formula. So those are our ions, I should say. So copper 1 and oxide, which is -2, which means that I'm going to need 2 coppers. Okay. And so my formula will be Cu subscript 2. I can't do the subscript. Okay. Let me get this a little bit bigger here. Okay. Cu copper subscript 2 oxide. And so the name will be copper 1 oxide. Totally different compound than number 7 that we did the first one. That's copper 2 oxide. Totally. The copper 1 ion, the copper 2 ion, totally different. One is a nice blue color solution if you put it in water. The other is a green solution. In fact, for many years growing up in Superior, I used to play in the Laguna, the water which had blue color. I thought that was the ocean. We thought that was cool. Playing this nice blue water. Turns out, I'm surprised I don't have another head popping out of my shoulder with all the chemicals up there, but it was copper ions we were playing with, and lead, had a lot of heavy metals, chrome. So a lot of that stuff was going on up there, but we thought it was cool water. Anyway, I didn't know what it was until I became chemist. I'm like, oh my goodness. All right, so the Roman numerals are good. Notice we did only use the Roman numerals when you have the metals that are not part of the 16. Okay. The anions name changes from whatever. Nitrogen becomes nitrite, oxygen becomes oxide, etc., etc. And these are for single atoms. We're not dealing with polyatomic ions, okay, which we will deal with here in the next page. All right, so the point to take away from here is to make sure you put them together with the correct number of cations and anions to equal in this case, a zero charge. All right, so when it comes to polyatomic ions. All right, so you're given this, and you look at this and you say, whoa, okay, magnesium, not a problem. All right, I see magnesium, I'm going to make it do the same thing we did before, find its ionic form. But this, you got an O and an H and then a negative. The fact that you're given the negative should give you a little flag and say, you know what, let me go to the polyatomic ions. And guess what it is? It's right there. OH negative. It has its own name. That is its name. If you have to name it, that part would be called the hydroxide. Okay? The hydroxide. Another hint that it's a polyatomic ion besides the charge, that you got oxygen, and then immediately following you get another atom, in this case hydrogen. So this is not the oxide by itself. In fact, you got a hydrogen bonded right next to it. Then a negative, you got a polyatomic ion. So we do what we did before, okay? And we break down the magnesium first. The magnesium is a +2. Group 2 element, it will have a +2 charge when it becomes ionic, okay? And then we got the OH, the hydroxide, the negative. So that means that we got to bring 2 of them together, 2 hydroxides. But this is where we put in our parentheses, okay? We don't change the oxygen and put a subscript oxygen or the hydrogen. This is the unit. You do nothing to the unit. You just put a parentheses around it and then a subscript to tell you how many of those polyatomic ions you need. And so you end up with this formula. And the name here would be called magnesium hydroxide. Simple as that. Again, not dihydroxide, but hydroxide, because we're still dealing with organic compounds, ionic compounds, excuse me when I say ionic compounds. which is a combination of a metal and a nonmetal. Is a magnesium metal? Yep. Is the OH nonmetal? Yep. It just happens to be an ion. Okay, here's PO4. You might think, okay, here's phosphorus. Maybe I'm dealing with phosphide. But like I said, you see phosphorus, then immediately following phosphorus, you see oxygen. Then you see a -3. Whoa, well, that should send you to the polyatomic ion table again. And it's not a good idea to go back and forth. It's a good idea to go back and forth here so you can get used to these. Be familiar with the polyatomic ions. Here's a PO4 -3. That is called the phosphate. You'll be surprised how much phosphate you ingest. It's found in everything, preservatives and all kinds of stuff. So, in fact, you ought to start reading some of the labels when you ingest something. You'll be surprised how many of these you're going to recognize name-wise. Okay. Just stay away from the chromate. You don't want to eat anything with chrome. That's heavy metal. It's not good for you. Lead, heavy metals. All right, so we got potassium, we know, it's +1, okay? And so since the phosphate has a -3 charge, I need 3 potassium, okay? So that becomes potassium phosphate. Let me write the names here for you. First one was magnesium hydroxide, okay? This one is potassium, metal name doesn't change, phosphate, okay? And you got the phosphate from the polyatomic table, okay? There we go, we got SO4. Again, you see the sulfur, you think sulfide, but no, because there's 4 oxygens bonded to it, okay? And then you got a -3, think polyatomic ion. So you go to the table and guess what? Its name is sulfate, okay? Then silver happens to be part of the 16, always has a +1 charge, always. So that means I'm going to need 2 of them to cancel out the -2 of the sulfate. And so our formula becomes NaAg2SO4. Notice I only need 1 polyatomic ion for the phosphate and the sulfate, so we don't need parentheses here. Only when you need 2 or more that you utilize a parentheses. So the name here would be silver sulfate. Also, too, you'll find a lot of sulfate in the foods that we eat. Part of it's a preservative. Okay. Now we have calcium and NO3. Again, you might think nitride, but there's oxygen. 3 of them specifically, and then you got that negative charge. You going to the polyatomic ion table, its name is nitrate, okay? Calcium is a +2 ion because it's in group 2. And so that means that we need 2 nitrates for every calcium. So this is where we put in the parentheses because we need 2 nitrates. You don't change the NO3. You put a parentheses around it and put a 2. Okay, some people will be tempted to say, well, why can't you make it N2O6? That's because that makes it into something else, not nitrate. Okay, so you got to do a parentheses. So this name is calcium nitrate. Okay. Notice again, no Roman numerals here, no prefixes here. We're dealing with ionic compounds. All the metals are part of the 16, so we're not using Roman numerals. All right. which is straightforward calcium. Straightforward silver, potassium, magnesium. Now we got Roman numerals, correct? Okay, so again, Cu Roman numeral 2 tells you you have a +2 charge. The CO3 minus 2 is the carbonate polyatomic ion, again found in your table. Now, in both cases, your copper's a +2. The carbonate is a -2, so it's a straightforward 1-to-1. Okay. Name would be copper, Roman numeral 2, carbonate. Okay. Copper 2, carbonate. Okay, the thing to remember here with polyatomic ions is to use parentheses when you need to use more than one polyatomic ion. Okay. All right, let's clear this up on tab. Okay. Now we're gonna learn to write ionic compound formulas. So we need to learn the names, which I've been introducing to you as we come along. Okay, so some of this may be a rehash, some may not. Best thing to do is really just to jump in there and do some examples. Okay, and remember that the fixed charge metals and the ones that are variables, because the ones that are variable charge, we need to use Roman numerals. Okay, we know, as I talked before, all the halogens, the ione suffix gets changed to IDE chloride. So in this formula, this is sodium chloride. It would be incorrect to say sodium chlorine, because chlorine represents the element chlorine, not the ion. The chloride represents the ion, and we are dealing with a ionic compound here. We got sodium chloride. So we got potassium and bromine as the compound. And we look at bromine, it's become ionic. So now, just like chlorine, it becomes bromide. So the name is potassium bromide. We got oxygen, which is now ionic oxygen, which now the name, as we've seen in numerous examples, becomes oxide. Magnesium remains magnesium. So we have magnesium oxide. Note again, we're not using Roman numerals here for potassium or magnesium because they have a fixed charge. So it would be incorrect to say magnesium Roman numeral 2 oxide or potassium Roman numeral 1 bromide. That would be incorrect because they are part of the 16. Here we got calcium and fluorine that at first glance you may think, well, that's elemental fluorine. That's fluorine, right? Because you see a subscript Q. But remember that there is a metal listed first as calcium, followed by the F2. And when that scenario happens, you're not dealing with fluorine, diatomic fluorine, you are dealing with ionic fluoride. Okay. So this is calcium fluoride. Notice the trend too, that as you see of all the examples, the metal is written first, name-wise, and also formula-wise. It's the metal first, and then followed by the non-metal. Okay. We got lithium, and then sulfur is sulfur's an ionic form, so it becomes sulfide. Okay, so this is lithium sulfide. It's a subscript 2 because lithium lithium itself is a +1 ion, and the sulfite is a -2 ion. So that means I need 2 lithiums per 1 sulfite. So we got lithium sulfide. And then here we got Ag, which is silver. And then Cl, which is, we would think chlorine, but the fact that we got the metal first tells us it's an ionic compound. So the chlorine name becomes chloride. Okay. All right. The thing here, remember, there's no prefixes like mono, di, tri, etc. Ionic compounds. Also, we only have 5 examples here, but you can move things around. You can combine potassium. Let me draw this. I could go potassium and oxide, potassium and fluoride, potassium and sulfide, and potassium and chloride. You know, that's 5 and 5. There's 25 more combinations here that you can do of compounds. All right. So you're starting to build up even more your database of chemical compounds. Okay. With the polyatomic ions, the thing is this. That is the name there. That doesn't get changed. Even though it's got a negative charge like the NO3 -1, its name for that unit is nitrate. Don't change it. Some people would name it as nitrogen trioxide. That's not even near right. Okay. It is nitrate. And so here you might think, well, how do I know that's a polyatomic ion? All right. Well, I can start with, okay, I know K is potassium, and I got 3 of them. But then I got phosphorus, okay? And I might think, well, maybe it's phosphide, right? But then right immediately following the single add phosphide, you got oxygen. So that's an indication that I'm dealing with a polyatomic ion. And so I can go now to the polyatomic ion table and look up PO4, and you'll find it. It'll be phosphate, which has a -3 charge, which is consistent with the 3 potassiums, because each potassium is a +1. Okay. And so that formula is consistent with potassium phosphate. Okay. The parentheses, the moment the parentheses is shown, got a question. I don't follow the question, Judith.
Like you said that when we see P and then we're like, oh, there's an O right after that.
Right.
How do I still just know that it's not just like a separate O? Is it because the P doesn't have a subscript? Like I know it's so, oh, this looks like the charges aren't matching up. Is that like you understand?
Oh, okay. Yeah, that's a good question. You'll find that the phosphorus, you'll find, let me pull up the polyatomic ion. If you notice that the nitrate, the nitrite, the sulfite over here on the right, that we have just a single nitrogen, single sulfur, single phosphorus. Okay. So it's 1. If there was a 2 or any number other than the 1 after for the nitrogen or the sulfur or the phosphorus, then there'd be something else completely. But that's a good assumption that if you see the phosphorus, the sulfur, and the nitrogen by itself, then immediately following you see an oxygen. You may not know what the number is yet, but you see an oxygen there. That indicates, that's a flag. Maybe I got a polyatomic ion. Then you look and see how many oxygens. Then you go to the polyatomic ion table, and you can see for sure if you got 3 or 2 for the nitrate versus nitrite.
Okay.
That makes sense?
Yes, it does.
Yeah. And that, that's like little tidbits here and there. It's not always 100%, but for Chem 130, probably 95%. All right. The other thing that to give you a hint that you got a polyatomic ion is a parenthesis somewhere in that formula. Okay, because we just went through scenarios that if you're going to use more than one polyatomic ion, that you use a parenthesis. So in this example here, you got a parenthesis, look inside, you got an OH, go to the table, you'll see the OH, its name will be hydroxide. You'll also notice that the hydroxide has a -1. So you come back to the formula and it says, I got 2 of these hydroxides. Is it consistent with the calcium? Certainly is, because the calcium has a +2 charge, right? And so the hydroxide each have a -1. So I got to put them together such that they equal 0. So it's consistent. The formula looks correct. And so its name would just simply be calcium, and then the name of the polyatomic ion, which is hydroxide. In fact, if you eat a lot of Tums, this is probably what you're eating. In fact, some of the Tums that you purchase, you'll see calcify. They'll say things like calcify, good for the bones. That's because you're eating calcium hydroxide. And keep this in mind, hydroxide is, quote, a base, BASC. Your stomach has an acid, ACID. And when you ingest calcium hydroxide, you neutralize the acid in your stomach, which is one of 6 chemical reactions we're going to talk about. So you're eating Tums, you're neutralizing the acid in your stomach. Or you can save some money and just drink some sodium bicarb, baking soda, a little water, because baking soda, I see the faces, but it's a base. The one thing is it's going to generate a lot of carbon dioxide, so you'll be burping a lot, but it's going to neutralize the acid. Okay, just in case you can't get to the store to buy Tums. All right. It's like that smart water. This. If you look at the label of smart water, they use distilled water, which you can go to any grocery store, buy a bottle of distilled water. Okay, it's labeled there, and all distilled water is just boiled water. They capture it, and then they come back and they put some magnesium. I'm like, whoa, that's what gives it the flavor. The salts, magnesium, sodium chloride. All right, let me stop it here. Because I think I'm going over some. I'll go over number 14. I think I only have one more. Zinc sulfate. Yeah, I'll just stop it there. Zinc sulfate. We're starting at 15. All right. So